So we've talked about convergence and divergence of general infinite series before, where there's like not a ton of specific requirements for what's inside the series, right? But there are specific forms of infinite series, specific formats called power series that are actually really useful. So these are when we combine our sequences with variables. So we're still going to rely on our same convergence test methods, but we can do a little bit more, and we can kind of like analyze these functions a little bit. So a power series is if x is a variable, then an infinite series in the form of the summation from a to n times x minus c to the n power equaling, right, they just expanded it out. So let's talk about what some of this means. So an, that's just, get my pen tools up here, right, so that's a sequence. Right, and then notice that it looks like you have two variables, but n is the indexing variable. So x is just standing in place of some number that we don't know, but n is the only thing that is changing as we evaluate the series. So we're still plugging in, like, this is where n is, this actually be 0. That's n is equal to 0, n is equal to 1, n is equal to 2, right? We're not changing the x, we're changing the indexing variable, the n value, as we continue to add terms up. So this is a power series, and we say it's centered around the x equaling c location. Just like how we do horizontal translations with normal functions, right? X minus c shifts us to the left or to the right, however many spots. So you also want to notice that there is an equal sign here, right? So this is not an approximation like Taylor polynomials. These are identities. These are things that are equal on both sides. So the infinite sum is equal to this series, right? So they're equal, they're not approximations, so you're not getting like kind of close. There's no error with these because we would be finding an exact sum if we can find the sum. So just something to pay attention to. So are these always true statements, right? Can you plug in any value of x? Well, nope, that would be too easy, right? So if you plug in a value for x and you apply your convergence test and you get a convergent series, great. But some values of x make the identities not true, so we're gonna get a divergent series. Again, we're just gonna be plugging different values in for x and seeing what works. So one of these three statements is always going to be true for a power series. It's only going to be one of them is going to be true at a time. So the first one is always true. So this is the bare minimum. So the series could only converge at x equaling c. So every power series has to converge at its center point, because if you plug in x equaling c into our formula, right, x minus c becomes 0 to the n power. So you're basically adding up 0 infinite times. So you're just adding to 0. It's like the dumb convergent case. It's like the basic one. So you could also possibly converge for all values of x. So you could plug in any real number and you'd still get a convergent series. The third case is where there exists an r greater than 0. So capital R stands for the radius of convergence, such that the series converges for x minus c less than r and diverges when it's greater than r. So that absolute value is just saying when you're within that distance of your center point. So for the right and the left side, the absolute value just takes care of the negative. But you're going to see what I mean in a second, because we're going to go through an example, obviously. So for the first example we're going to do is we are going to find the radius and interval of convergence, and we're going to make sure to test the endpoints independently. So what you're going to do for finding your radius of convergence is you're always going to use the ratio test. So we're going to do the ratio test. So we're going to say, okay, the limit as n goes to infinity of the absolute value, and we're going to plug in n plus 1 first, right? So we're not plugging it in for the x's, we're plugging it in for the n's. Right, and then I'm going to times that by the reciprocal of my function. Oops. Okay, so now just to do a little bit of limit stuff. How much space do I have over there? I have lots of space over there. Okay, so we got the limit as n goes to infinity. Okay, let's just kind of group things. So let's see, my negative ones, right, are really not going to matter because of the absolute value. But I would get negative 1 to the first power, but that's just going to cancel out. I'm going to get x minus 5 to the first power, right, if I take care of that part. And then that part's going to cancel out. And then times n over n plus 1 times, let's see, 2 to the n over n plus 1, that's going to give me 1/2. Okay, right, because that's going to go away. There we go. So what that is going to equal, right, is the limit as n goes to infinity. Well, hang on, we don't need the limit symbol anymore. Let's just take the limits. Let's just do it. Okay, so the limit of each part, right? So if we do it independently, so the limit as n goes to infinity, we're not looking at x's, so we're just going to get the absolute value of x minus 5 times, okay, I need a little bit more space than that. So the limit of the middle part, the n over n plus 1, as n goes to infinity is 1. The limit of 1/2 is 1/2. So we get that the limit is just 1/2 times the absolute value of x minus 5. So you're like, okay, how do I use that? So, right, we know the ratio test says we have a convergent series if the limit is less than 1. So we're going to set that less than 1. So if we think back to what we just said about our true statements, the radius of convergence, we have x minus c here. So in this case, right, our c value is 5, right? The absolute value of x minus c is the same thing as the absolute value of x minus 5. So we want to get that alone. So we want this whole statement to kind of pop out in our solving for the ratio test. So we want to see x minus 5 is less than something, and that something is going to be our radius of convergence. So if we go back here, I want to get absolute value of x minus 5 alone, so I'm going to multiply both sides by 2. So this tells me, right, boom, boom. So we're going to get that, oops, the absolute value of x minus 5 has to be less than 2. So that tells me that my radius of convergence is 2. So if we think about what that means on a number line, we were centered at the point 5, right? So if I go 2 spots to the right, I'm at 7, 2 spots to the left, I'm at 3. So we have to be careful when we're finding the interval of convergence. We want to know, do you include or not include the endpoints? So you have to test them separately. So after the ratio test and you find your radius of convergence, we are going to test the endpoints, and you're going to test them each separately, or independently, as the problem said. Right, so my first endpoint was x equaling 3. So all we're going to do is we're going to go in and we're going to say, hey, we're going to plug in 3 for x. So if I plug in 3 for x, I'm going to get the series from n equaling 1 to infinity of negative 1 to the n plus 1. 3 minus 5 is negative 2 to the n over n times 2 to the n. Okay, so now it's just a little bit of algebra manipulation, and then we're going to apply our series stuff, right? So negative 2 to the n, I can rewrite that as negative 1 to the n times 2 to the n. So if I do that, right, my 2 to the n's cancel out, and I'm going to add another n over here. So I'm going to get negative 1 to the n plus the 2n plus 1 all over n. Okay, so then 2n plus 1 is always an odd number, and negative 1 raised to an odd exponent is always just negative 1. So we're going to say, okay, this is equal to negative 1 over n. So now we need to decide, does this converge or diverge? If it converges, we include the 3 in our interval. If it diverges, we don't. So this series is going to diverge, right? Because it's the harmonic series, right? You can say by the p-series test or by the harmonic series because it's assumed that you know what that is, right? It's just negative 1 times the harmonic series. The harmonic series diverges, so this diverges. So we are not going to include the 3 in our interval of convergence. So if we go over here for our interval of convergence, interval of convergence, and I wish I could spell. Right, so we know at 3, we're not including the 3, and then we're going to go back over here and we're going to test when x is 7. Right, so I'm going to plug in 7 instead of 3 now. So if I plug in 7 minus 5 is 2 to the n, we can see right away that those 2 to the n's are going to cancel out. So we get the alternating harmonic series here. So this converges by the alternating series test. All right, this is just the alternating harmonic series, which we have proven before does converge. Right, and if you're not positive of that right off the top of your head, right, you're going to apply your convergence test. So we are going to include 7. So we're going to say our interval of convergence is 3 not included to 7, which is included. So let's go ahead and do another one. So we're going to find the radius of convergence. So we're going to do the exact same thing for this series. So it looks a little bit more complicated. We got some factorials going on. We got some funky exponents on x. Totally okay. So one thing to notice here is we don't see an x minus c, right? So that implies that c is equal to 0. So when we're looking to find our radius, we're looking to get the absolute value of x less than r. So to do that, we're going to go ahead and apply our ratio test. So we're going to do the limit as n goes to infinity. The absolute value. So since it's absolute value, I'm not even going to worry about the alternator there because it does not matter. Got x to the 2 times n plus 1 all over 2 times the n plus 1 factorial times the reciprocal of the original. Okay, so let's do a little simplification here. We got the limit as n goes to infinity of, I'm going to get x to the 2n plus 3 over x to the 2n here. Nope, plus 1, because apparently I didn't type everything. There we go. I was like, that doesn't work. Okay, so then we've got 2n plus 1 factorial. We're going to get 2n plus 3 factorial. So that's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial if we break it apart. So then the factorials cancel. If I simplify my x's, I'll just go down here. We got limit as n goes to infinity. We're going to get the absolute value of x squared over, right, 2n plus 3. Times 2n plus 2. So remember, we're taking the limit with respect to n as n goes to infinity. So as n goes to infinity, right, there's no n's in the top, so our limit is 0, right? And by the ratio test, right, we know that 0 is always less than 1, so that's always a true statement, right? So because it's always true, that tells us that our radius of convergence is actually all real numbers. Or you can write it with the fancy double bar capital R for all reals. And because it's all real numbers, your interval of convergence, which I'm going to abbreviate as IOC, right? It's all real numbers. So it's just negative infinity to positive infinity. There you go. So, of course, we have special types of power series, and that's going to be bringing our Taylor series back into play. So our Taylor polynomials, we're just going to extend out to infinity. Instead of stopping at a specific number of terms, we're going to let them go on forever. So we know how to put a Taylor series together, right? We know that it's x minus c to center it at a c value, and that we're taking our derivative and dividing it by that n factorial as we go on. So it's just written out here to infinity. You can see here the nth term. This is called the general term. right? It's a general term because you can plug any value in for n and find that term. And if we want to write it as a summation, this is actually incorrect. This should be a 0. I made so many typos with these today. It should be from n of 0 to infinity, right? And it's the same as the general term, and then you just put the summation in front of it. And we know that if C is 0, if you're centering a Taylor series at 0, it's just called a Maclaurin series. It just gets that special name. So before, our Taylor polynomials and our Maclaurin polynomials, they were approximations. They would get us close to the actual value of a function at that point, but we couldn't actually say that it was equal to. So since we're letting n go out to infinity now, right, the sum from 1 to infinity or 0 to infinity, we're just going to be like, okay, like that means that it's exactly the same, right? It's an equal sign, it's an identity instead of an approximation. So that's kind of cool because that means that for really complex functions that maybe you couldn't have evaluated by hand, you can actually change everything to a polynomial. So that's all this is doing. Okay, so based off of what we've done with Maclaurin polynomials, we're going to find the Maclaurin series for y equaling e to the x. So we learned for Maclaurin polynomials, we're writing out the first couple of terms before, we knew that e to the x was equal to, right? Actually, hang on, you know what? Let's just do the math for this one real quick in case we need a refresher. So we tend to want to write out the first couple of terms. So in general, writing out 4 non-zero terms is good, and then jump to the general term. So let's see, our function is y equals e to the x. All right, we know all of our derivatives are e to the x. And if I plug in x of 0, right, all of these are just going to be 1s. Right, so my m of x, my Maclaurin series, my function is going to be, right, the first value, so 1 plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x cubed over 3 factorial, right, plus we could go out to the fourth term. So we have 4 non-zero terms, and then we're going to take it out to the general term. So that would just be, it's always positive, so we don't have an alternator put in here. So it's x to the n over n factorial, right? And that would equal the sum from 0 to infinity of x to the n over n factorial. And we have to start it at 0 because we want to be able to plug in the first, 0 and get a 1 back, right? So if I plug in n of 0 here, right, x to the 0 power is 1, and 0 factorial is actually also 1. So we get 1 over 1 and 1. It gives us back our first term. Okay, so now they've also asked us to determine the radius of convergence. So let's go ahead and do the ratio test. So we got ratio test going on. So we're going to take the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Okay, so then if we do a little bit of algebra manipulation, right, x to the n plus 1 over x to the n is just x, and then n plus 1 factorial is just n plus 1 times n factorial. So then those cancel out. So we get left over n plus 1. So remember, we're taking the limit as n goes to infinity. So just like our last example, this limit is actually going to equal 0, and that is always less than 1. So our radius of convergence is going to equal all real numbers, and our interval of convergence is all real numbers, so negative infinity to positive infinity. So just going to do a couple more, and then we're going to be done with this part of the video. Right, so now we're going to use that previous example. So we had that e to the x, right, was equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus our general term. Right, just copying down our work from the previous problem. And we're going to use this to find the Taylor series for e to the 5x, and we're going to center it at c equaling 2. So those are the only things that are changing. Okay. So, right, the 5x just replaces the x. So all I'm going to do is say, okay, this is the same thing, but we're going to replace it with 5x. So I've got 1 plus 5x plus 5x squared all over 2 factorial plus 5x cubed over 3 factorial, right, plus 5x to the n over n factorial, right, and then out to whatever. Now, if I want to center it at 2, all of my x's should look like x minus 2's instead of an x, because if it's just an x, we assume it's Maclaurin, it's not centered anywhere. So now to center it at 2, so c equaling 2, all I'm going to do is say, okay, I've got 1 plus 5 times x minus 2, plus, if I want, I can make this a 25 or a 5 squared. We'll write it that way, 5 squared times x minus 2 squared over 2 factorial plus 5 cubed times x minus 2 cubed over 3 factorial plus out to our general term, because it asked for the first 4 non-zeros, so our first 4 non-zeros are done, and now our general term is just going to be 5 to the n power times x minus 2 to the n power all over n factorial. And technically, I just need to move this over. Right, technically this does keep going forever, so I would add a plus ... if I was just handwriting my answer for the full series. Okay, we're going to do one more. So one of the cool things about these is that if you know your Maclaurin polynomials and Taylor polynomials really well, you can actually use them to help recognize what a series is and find the actual sums. So we're going to find the actual sum of the following series. So typically we can only find the actual sum of geometric and telescoping, but if you can recognize a Taylor polynomial as what the function it represents is, you can evaluate it. So if I look at example A, I have 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus, right, you can read. So if we look at this, right, we have all of our even terms, right, and they match here. And then we also are alternating signs, right? So if you have your notes from Maclaurin polynomials handy, or if you just have these memorized, because hopefully we do, right? So this is going to be our representation for cosine. This is the cosine function, right? So that's the same as the cosine polynomial for Maclaurin polynomial, right? It's just keeping going forever. So this is the cosine function, and they've plugged in pi, right? So instead of having an x to the squared in the top or x to the 4th, we have replaced x with pi. We know that cosine of pi is -1, so the sum of this series is -1. Okay, let's try another one. We have 1 plus the natural log of 4 plus the natural log of 4 squared over 2 factorial, right, all the way out. So this is actually one that we wrote down before. This is the series for e to the x. So this is really saying e to the natural log of 4, and e and natural log cancel out, so the answer is 4. Right, so if you can recognize what the pattern is, and that's why we want you to know those basic ones, you can actually pull it back and find exactly what the function is equal to, because you can evaluate those functions. So C is a little harder. So we have our odd powers, right, because the power of 1, power of 3, 5, 7. So it almost looks like it's alternating signs. So alternating signs and odd powers kind of signals that this is sine, right? Alternating and odd powers is sine. So we have some extra stuff in the top, though. We have 2 here. So normally sine of x is just equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, right? So now it looks like they've multiplied it by 2. So we're just going to put parentheses around that. And then they've plugged in pi over 6. So that's telling us that this function is actually 2 times sine of pi over 6. So pi over 6 is equal to 1/2. right? And then 2 times a half is just 1. So final answer there is 1.